The laser from Măgurele, matter made of light. How is this possible, sir? This is what the laser from Măgurele is being prepared for, and the laser from Măgurele is no longer the most powerful in the world. The SUL laser from China has surpassed it. But hey, what matters is not the power, but the energy density, and here the laser from Măgurele is doing very well. Here's the summary. In the first part, a few words about the laser, and especially, we will compare it with the other powerful lasers in the world, many of which are also trying to do the same thing. Then theory. What is the quantum vacuum? How is it filled with pairs of virtual particles, for example, electron-positron? And how can these virtual particles be brought into reality with the help of a very strong electric field? We will continue with theory, specifically what virtual particles are, and most importantly, the mechanism we need, namely the Breit-Wheeler mechanism. And then we will continue with an experimental demonstration of this experiment, which manages to bring particles from the quantum vacuum into reality, electrons and positrons. An experiment that took place almost 30 years ago. In the last part, about the laser from Măgurele, what it wants to do differently and how it aims to improve on an experiment from 30 years ago. Especially what was announced recently, since they've already demonstrated the first stage of this new experiment. What is the laser from Măgurele? Basically, it's not very different from a laser pointer, meaning it's a source of coherent light, because all the light around us, including the one coming from stars, is made up of particles called photons. It's just that the light coming from the sun or from stars is called incoherent because those photons are not aligned with each other. The light from a laser is coherent light. The photons are aligned in phase. We can imagine them like soldiers marching in sync. However, the laser at Măgurele is a pulsed laser. That means it sends out pulses of energy. In this case, the energy pulses are about 200 joules each, and these pulses are sent once every minute. So you start the laser, 200 joules, you send the energy pulse, stop the laser, wait, and then you fire the next pulse after a minute. This already debunks some myths. Why? Because 200 joules isn't much energy. 200 joules is enough energy to heat 50 grams of water so that the temperature of the water increases by 1 degree Celsius. So, if a dynamic tank or an airplane comes, there's not much you can do with this laser. The laser from Măgurele is not the kind of laser used to melt tanks, airplanes, and so on. Why is the Măgurele laser called the world's most powerful if its energy is actually too low? Because we're talking about power, meaning the energy delivered over a period of time. Well, the laser delivers this energy in 20 femtoseconds. 200 joules isn't a lot, but delivered in 20 femtoseconds. That means a very high power. In that very short time, the power delivered by the laser is extremely high. Just to get an idea, yes, 20 femtoseconds. 1 femtosecond is 10 to the minus 15 seconds. And the electron orbits around a nucleus in a few femtoseconds. So basically, this laser delivers a power of 200 joules, yes, in just a few periods in which the electron manages to orbit around the nucleus. That is, in an extremely short period. Well, if we divide the energy by the period of time, we get 10 petawatts. So we're discussing the laser's power, right? Which, mind you, is delivered over a very short time. We can better say that the brightness of the laser is very high, meaning the laser is off, and then when it's turned on for a short period of time. If you looked at it, God forbid, the brightness of the laser is very strong. It shines with 10 petawatts, which is essentially about a tenth of all the light that reaches the surface of the Earth. The laser at Măgurele is one of the many high-performance laser complexes that are being built around the world right now. You could say that this field exploded about 10 years ago. Ever since, among other things, Herr Armuru's research showed that this is possible, Herr Armuru received the Nobel Prize, and in the meantime, things have progressed. Romania, France, Czechia, China, the United States, Russia, Korea, all these countries. They are trying to build lasers with a very high power, so with a very high brightness. Many of these lasers are being built through companies. In this case, in Romania, for example, the laser was built by the French company Thales. This essentially means that the laser at Măgurele is not a Romanian state laser. It was not built by a team or a company from Romania. Romanian workers participated in the installation of the laser, but the project was actually built by the Thales company from France, the Thales company, which also took part in the construction of other lasers, such as the Apollo laser. Even if not entirely, but through certain elements. So we're talking about ecosystems, and that's very important to mention. Ecosystems. The laser at Măgurele is part of an ecosystem of very powerful lasers all across Europe. The ecosystem is called extreme light infrastructure. That's where the name extreme light infrastructure comes from. And we have such lasers built not only in Romania, but also in the Czech Republic and in Hungary. Again, recently one of the beggars who are now in Hungary was caught. They won Nobel Prizes precisely for their contributions to such lasers. And again, it's important to add that by being part of such lasers, by being part of ecosystems, they continue to be part of ecosystems. By providing this infrastructure for research teams. So in the case of the laser from Măgurele, the laser from Măgurele is not only for Romanian researchers. In fact, there are many, 3 in the team from Bucharest, and the laser from Măgurele is made available to teams from all over Europe and even from all over the world who have the right to receive so-called time, meaning beam time, as it's called. That is, to write a project in which they tell the people at Măgurele, good people, I want to do this experiment, like this, like this, like this. Please allow me to come to your laboratory and, together with you, of course, to do these experiments. Today's article, for example, which also presents the results from the Măgurele laser, yes, is a collaboration done not only at the Extreme Light Infrastructure laser in Bucharest, but also at the Apollo laser in France. And on the list of researchers, there are only Romanian researchers, yes, and researchers from France, Portugal, Sweden, and even from the United States and Israel. It is perhaps a very good example that shows that when you want to do such experiments today, investigations at the edge of knowledge, yes, you are put in a situation where you can do this through transnational projects that go beyond borders, both through the research teams you have and through the projects you carry out. Yes, even so, because the subject we are talking about today, generating matter from light, is essentially a topic with Nobel potential. Yes, that's why there is competition. Even though we're talking about collaborations, there is competition among different research groups all over the world. Here is the list of lasers under construction, which, once completed, will need to have powers of over 10 petawatts. Yes, the laser at Măgurele is one of the few that is ready. Just the laser, mind you, not the gamma source, which is still under construction and delayed, but the LNP laser at Măgurele is ready. I also forgot to say it's called LNP from nuclear physics. Yes, and it has already reached 10 petawatts. However, we also see France, Apollon, and the Czech Republic on the list as well. 10 petawatts is part of the Extreme Light Infrastructure SOLF group from China, 10 petawatts SEL, a laser from China that aims to reach 100 petawatts, which is 10 times more, and it is under construction. I haven't read much about it lately. I have the feeling that there are problems everywhere, especially with these ones. Lasers like SEL targeting 100 petawatts face many problems. Because I don't see such announcements from month to month, I would say yes. We also have other lasers on the list, and what caught my attention was the Vulcan laser, which will be extended to 20 petawatts, and the laser in Russia, which aims to reach 200 petawatts. To be honest, I haven't heard anything. I think they're too ambitious over there, and I have it here in front of me. The SOLF laser from China. Here you see an announcement that was made in 2017 by a Chinese news agency. Yes, in which they said that the SOLF laser had already reached 10 to the third power petawatts. So that would mean before the laser from Măgurele, which made its announcement around 2019. So this Chinese laser would have been the first. And I was interested in this story. Was it true? Is it true today? and I looked for the original article, but I didn't find it. I found an article from that period, which you can see here, where it says that the laser would have the capacity to deliver 10 petawatts. So, it might be that in 2016 they didn't actually deliver this capacity, but rather demonstrated by measuring the respective components that the laser has this capacity. However, more recently, in 2021, yes, so at the second one, let's say, after the Măgurele laser announcement, China's SUL laser still claims 12.8 petawatts. This is an article I found and, well, how should I say, it's accepted in scientific journals, so it's peer-reviewed, so essentially it should be true. And if indeed, in 2021, the SUL laser from China reached the value of 12.8 petawatts, that would essentially mean that it has already surpassed the laser from Măgurele, which announced something like 10, I don't remember, 8 petawatts. So, would the SUL laser from China then be the most powerful in the world? I dug deeper because I said, is it really like that? And I found this article from 2025 which reviews all the high-power lasers in China. And here, again, this article refers to the previous article and again claims that the SUL China laser did indeed reach 128 petawatts. So, essentially, it would now be more powerful than the laser at Măgurele. But basically, both lasers are 10 petawatt lasers. So what experiments are being done here? These can also be done on the other side, under different conditions, but I don't know what the repetition rate is. But on the other hand, I was interested in that powerful laser, SEL from China, which should reach 100 petawatts. Well, over there, on the other hand, I haven't found any measurement results, I haven't found anything recent. So that means, as I mentioned, I believe that they still have major delays in construction and problems. Because it's not easy to build such a laser, and very importantly, it's not easy to focus it. Now, why is it not easy to build them? Let me step in here just a bit. Essentially, because these lasers are amplified through active amplification media, which can be crystals. And you can't have a very high laser beam density passing through that medium, because it can damage it, cause cracks, break it. And then, in order to amplify in that amplifying medium, a laser beam, which essentially is very powerful. What you need to do is to make that amplifying medium, that crystal which amplifies the laser, you need to make it very large. That means both the laser beam and the amplifying medium are very large. Well, and these crystals, which have a very large radius and need to be grown in order to allow and to amplify the very powerful laser beam, yes, growing large diameter crystals is difficult, as I mentioned. In short, one of the problems that I think lasers in China have, including this 100 petawatt laser, and I said it briefly, without preparing, because it just so happens that indeed in the 1990s I worked in a crystal growth laboratory for laser active media at Măgurele, under the leadership of Professor Voicu, who is now a member of the Romanian Academy, and, well, from him I understood that it was okay. Growing a crystal medium with a small diameter ensures uniformity and precision, but it's different from growing a standard crystal medium. Yes, a crystal through which you amplify the laser beam, and for it to have a very large diameter, because then you can have non-uniformities in the same crystal, so problems. If the laser beam isn't amplified as desired, it distorts the beam's shape and other properties. And let me get back to this question. What is currently the most powerful laser in the world? Yes, I also found an announcement somewhere that the Apollon laser has reportedly reached, attention, 10 petawatts. So it would be the third laser after the Eli laser, after the Chinese laser, and after this one it would be the third, after the other two. Again, I wanted to see the original article and I couldn't find it. On their website, I saw they announce each time the laser reaches 1 petawatt, 5 petawatts, etc. From that, I realized it never actually reached 10 petawatts. So that means that in practice we currently have 2 lasers in the world that have reached 10 petawatts. The laser from Măgurele and the laser from Sulf, China. So the 10 petawatt one, not the 100 petawatt one in... A recent article, the physicists from Măgurele, in collaboration with other physicists, announced that they have completed the first stage of converting light into matter. how can we obtain matter from light? We define matter here in the context of this video, yes, because light could also be called matter. But in the context of this video and in a popular context, we define matter. Let's say the building blocks of atoms. This means electron with arcs, which in terms of physics, these particles are called fermions. Light, on the other hand, is made up of some particles called bosons. They have different statistical properties in quantum physics. But that's not what interests us. We're interested in how we can create matter from a beam of light, meaning fermions. Now, the process I'm going to try to explain uses essentially an intermediate step, namely the quantum vacuum. That is, we imagine that there's nothing in the vacuum, but in nature's vacuum, there is something, namely virtual particles. They are brought to life for a short time through, well, certain quantum processes. And what interests us in particular are the electron-positron pairs. The positron is the antiparticle of the electron. So, in this quantum vacuum, for a very short time, pairs come to life. Don't forget about the electron-positron particles, which then recombine and disappear. Alright, this is the quantum vacuum. It's like a soup bubbling with these electron-positron pairs that come. The electron-positron appears, recombines, and vanishes back into the quantum vacuum. In short, the idea we're using is that we use light as energy. Yes, to put this energy into the quantum vacuum and to separate the electrons and positrons that form pairs. Yes, let's separate them in such a way that the two particles, the electron and the positron, which were in the quantum vacuum, move far enough apart so that they no longer recombine. And in this way they will become real particles. Well, I talked about this in storytelling physics, and here you can see a drawing where I drew pairs of virtual particles. Yes, and we see them settle between the plates of a capacitor. The idea is to separate the electron and the positron from the virtual pair, so matter and antimatter. To separate them at a large enough distance so that they no longer recombine. And this is done by means of a capacitor. You see the electric voltage there, you see that an electric field is formed, and because of the electric field, an electric force also appears. And as we know, the electric force is Q times E, meaning Q is the charge. One side has a positive charge, the other has a negative charge. So because of this electric field, electric forces appear in opposite directions, and the electron and positron will separate. Well, and how is this calculation done? Well, it starts from the idea that a virtual electron-positron pair usually has the size of the Compton wavelength, 10 to the minus 12 meters. Why it's that size is another topic in physics. But to bring them into reality, yes, you have to separate them by a distance greater than the Compton wavelength, 10 to the minus 12 meters. But you also have to do one more thing, namely the energy you bring with the laser and put between the particles, yes, must be transferred to the rest mass of the electron and the positron. Now this leads you to the result that the particles, once separated, will have speeds close to the speed of light. They will have relativistic speeds. And then the calculation goes as follows. We apply an electric field, and we're interested in how strong the electric field is. In such a way that if we start with an electron and a positron close together and we separate them using the electric field, yes, after they reach a distance between them greater than the Compton wavelength, 10 to the minus 12, they will also have speeds close to the speed of light. Well, if you do that calculation, you'll see that the electric field required, as calculated by me here, is about 2 times 10 to the 17 volts per meter. The real value is 10 times higher, calculated properly, and this real value is called the Schwinger limit. So, after the physicist who investigated these phenomena, and the required value is about 2 times 10 to the 18th volts per meter. And when I wrote the book, Physics Told Us a Story, the laser at Măgurele was just an idea? Yes. So it was, let's say, under construction. I don't know if the construction had started, but it was just an idea. And it's very interesting that I talked about the laser in the book, precisely with the idea that it would perform this experiment. Why a laser? Because Essentially, a powerful laser has a strong electric field, and then the strong electric field could generate that Schwinger effect I was talking about. However, be careful, the laser needs to be focused, because if the laser beam is very wide, on each small part the electric field is weak. But if you focus the laser into a point, into a very small area, on the order of micrometers, yes, then all the electric fields add up coherently because the laser is coherent light, and in that area you get a very strong electric field. So, physicists have calculated how well you need to focus a laser, yes, in such a way that you reach that Schwinger limit for the electric field. And this is what they tell us. That laser needs to be focused well enough so that the energy density is about 10 to the power of 29 watts per square centimeter. And this is where it comes in. The second very important problem with all these high-power lasers is that they need to be focused very well. And in order to be focused very well, they need to have some focusing mirrors. They need to make sure that the laser beam I was talking about at the beginning, which is amplified by the laser crystal, yes, and which is very wide. It needs to be as uniform as possible so that the focusing phenomenon is good enough. Well, when it comes to energy density, the laser at Măgurele performs very well. Because the beam is focused into a small area, the energy density reaches values of 10 to the power of 23 W per square centimeter. Some of the highest in the world, which, as far as I found, have only been announced by the Korean laser corals with 4 petawatts in 2021. However, be careful, because to achieve the Schwinger effect we need 10 to the power of 29 W per square centimeter, while right now we have something on the order of 10 to the power of 23 W per square meter. So we're already about 6 orders of magnitude away from the theoretical limit. Well, then the question is why? Could we hope to obtain new matter from light with these lasers if their energy density is about 6 orders of magnitude lower than the theoretical limit? How is that possible with lasers? The answer is that it can be done by using a mechanism. In fact, there are 2 mechanisms that bear the names of the physicists Breit and Wheeler. However, to understand the Breit-Wheeler mechanism, we need to take a step back in theory. Let's briefly discuss virtual particles. The concept... I've been fascinated by virtual particles since hearing about them from Richard Feynman. And it basically says that a particle travels along multiple paths at the same time. Yes, let me just say a few words, that's so I can pray. Maybe I'll bring it out again. That's how it is. So what I want to say is this. In classical physics, particles are little balls. That's how we can imagine them, like little balls. In quantum physics, at first, the quantum motion of particles is described by a probability wave. And that's what you see in this graph. Yes, we have a probability wave that tells us roughly where the electron is with certain probabilities, and this probability wave undergoes a diffraction effect. And because of this, in this diffraction effect, we will see interference fringes on the right side. Whether we do this experiment with light or with electrons, in the case of light, the wave is the light wave. And in the case of electrons, the wave that diffracts is the probability wave of the electrons. Physicist Richard Feynman tells us to reinterpret this wave interference through virtual particles. His statement is shown in this drawing. So let's just say we make some holes in the diffraction panel, right? What will we have then? Well, essentially, we'll have a wave that passes through multiple locations and then recombines on the diffraction panel. He tells them this. Let's not look at it this time as if we have a single wave, the probability wave. But let's imagine that each little piece that enters, as shown in the drawing, is a small wave. A pilot wave of a particle that would pass through there in Feynman's interpretation. So, we will no longer discuss where we are, and we will talk about virtual trajectories that the same particle passes through. Yes, and each virtual trajectory has a wave associated with it, which we can call a pilot wave. So, well, regarding the name, that's another discussion. We see here, for example, 4 such trajectories that the particle could have. On each of the trajectories, the particle carries its wave with it, and at the end, these waves recombine and give us the interference fringes. This essentially is a reinterpretation of Christian Huygens' principle. What do we take away from this? We leave with a reinterpretation of quantum mechanics. We no longer say that an electron is guided by a probability wave, and that wave interferes and, in the end, gives us those diffraction patterns. We say that an electron can travel simultaneously on multiple virtual trajectories, and on each virtual trajectory, it carries its pilot wave. And in the end, we calculate the probability amplitudes based on these phases, and we see what is the probability of finding the electron in one place or another. And Richard Feynman manages to reinterpret all of quantum mechanics in this way. That is, he tells us that this world can be described through these virtual particles that travel on virtual trajectories. And here we see such a reinterpretation where we see how two electrons, the lines with arrows, repel each other due to the electromagnetic field. We know that two electrons repel each other because of the electrostatic repulsive force. In Feynman's interpretation, pay attention, yes, we're talking about two electrons moving through space, and as they move through space, so upwards in time on the axis, they exchange between them. A virtual photon, meaning a virtual particle of the electromagnetic field. And because of this exchange of virtual particles, the two electrons will move away from each other. To get light from matter, we don't need to create very strong electric fields, but we need to use the virtual interactions between these particles. In this case, you can see here such a process which is called the Breit-Wheeler process, where two photons, this time, pay attention, these are two real photons they have, but here you can see. Thus, they interact, and as a result of their collision, an electron-positron pair is formed. The process that takes place is detailed here, and you can see that it happens through a virtual electron which is exchanged between the two photons. So, Breit-Wheeler tells us, in the first instance, how we could obtain these electron-positron pairs from the vacuum. How? Well, we have two beams of gamma rays, because each of these beams, the gamma rays, are electromagnetic, right? Each gamma ray photon must have an energy greater than the rest energy of the electron. So that means it has to be over half a mega electron volt. And then we need two gamma rays that we focus very precisely at one point, at that intersection point. They will exchange virtual electrons, let's say from the quantum vacuum, yes? And then generate positron electrons, which will become real through this process. The problem with this process is that the scattering cross-section, so basically how well you need to focus the two gamma rays, is very low. And the optics for these gamma rays is not that well developed. So in other words, with current technology, we can't focus gamma rays that well in such a way that we have very efficient scattering between the two photons and obtain positron-electron pairs in a large enough number so that we can measure them in the laboratory. And this is where the second suggestion of Breit-Wheeler comes in, namely the multiphoton Breit-Wheeler process. We see it in this Feynman diagram where, pay attention, this time goes from left to right. And we see here how a gamma photon with very high energy interacts with several laser photons. This time they are visible light lasers, infrared and so on, so with a very low frequency. This interaction occurs via virtual electron exchange. Yes, and if we go to the right, we see that as a result of the interaction, an electron-positron pair is produced. So the electron and positron come from the quantum vacuum into reality. Every time I see such a Feynman diagram, I can't help but think about this very strange interpretation that we can read. Like that. Yes, on the left side, so at the beginning of time, we have the gamma photon and the laser photons, and on the right side is the future. And what we see at the top, we see the positron traveling into the future. But it can also be interpreted as an electron going back in time. So there we have an electron that is going back in time. It virtually mediates the interaction between the gamma photons and the laser photons, and after that it goes forward in time as an electron. The process by which matter is generated from light through the quantum vacuum. Yes, it was demonstrated almost 30 years ago in a famous experiment called Stanford Linear Accelerator Center E144. Here is a picture of the Stanford Linear Accelerator Center experiment. Let's discuss it in detail. The beauty of physics, right? In the upper left corner, we see those two theoretical processes that are at the core of the experiment. In the upper right corner, we see the multiphoton Breit-Wheeler process As I said, time moves to the right. So, there we see how a gamma photon should interact with the laser photons to produce the electron-positron pair. On the left side, we see how that high-energy gamma photon was produced. We see here that we have some electrons that this time have high energy, interacting with some regular laser photons. And through an effect called the inverse Compton effect, yes, they generate a low-energy electron this time and a gamma photon with very high energy. Because of this, the phenomenon is called the inverse Compton effect, because at the beginning, the electron had high energy, which it transfers to the high-energy gamma photon. How did the experiment take place? Well, in the experiment, very high-energy electrons were combined and made to interact with some laser beams. A powerful laser with an energy density of 10 to the power of 18 watts per square centimeter. As we can see, this energy density is lower than the energy density of the laser at Măgurele. The electrons in this experiment come from the left side and are electrons produced in a regular particle accelerator. I don't know if it's linear or circular, but it's a regular particle accelerator, which is regular in the sense that, well, regular for someone who has particle accelerators, right? Which accelerates electrons to pretty high energies, 46 GeV. So how does the experiment take place? Well, on the left side, we see the electrons coming from the particle accelerator in pulses, in pulsed beams, and in green we have the laser, which also comes in laser pulses. The energy of the laser is quite high. We can see there that the energy density is the laser is focused in an area of a few micrometers, and in that area the electron beam comes in and the two beams are synchronized in such a way that they interact in the micrometer area. The first miracle happens in the contact area, namely the electron that comes with GeV energy starts to absorb many photons from the laser beam and becomes a virtual electron. And this virtual electron further disintegrates into a regular electron with lower energy and a gamma photon that has very high energy. In this case, 29 gigaelectron volts. In the second part, we have the second miracle process, meaning these gamma photons, which already have very high energy, 29 gigaelectron volts. They are still there in that laser area, and then they start to interact with the photons from the laser beam through virtual electrons. And as a result of these interactions, this is the multiphoton Breit-Wheeler process. As a result of these interactions, electron-positron pairs are created. And as you can see from the drawing, electron-positron pairs appear from the interaction area. According to the experiment's results, not many positrons appeared. Because out of 20,000 attempts, so out of 20,000 moments when the two beams were aligned, in total they barely managed to detect 100 positrons. The main reason is that, in the case of the Breit-Wheeler interaction, that gamma photon has to interact with the laser photons over a distance that is smaller than the Compton wavelength, and over that Compton wavelength distance, it has to interact with a lot of laser photons. In this case, the high energy gamma photon interacted with about 46 laser photons. And because of this weaker interaction, not so many positrons were obtained, 100 positrons in 20,000 attempts. But it was a successful experiment. It showed that indeed matter can be obtained from light through the video process. Honestly, I haven't looked for more recent articles that reproduce this result. I saw that most articles refer to this result as if it were truly exceptional. What we want, however, is more positrons so that we have a result as clear as possible. In order to have more positrons, this Breit-Wheeler process needs to be more efficient. That means those gamma photons need to interact with more laser photons over that length, which is essentially the Compton wavelength. How can they interact with more laser photons? Only if the laser is more powerful. Well, the laser at Extreme Light Infrastructure is more powerful than the laser at Stanford Linear Accelerator Center. And then we expect that if we repeat this experiment with the laser at Extreme Light Infrastructure, we will have many more positrons. The problem is that the particle accelerator at Stanford Linear Accelerator Center, which stands for Linear Accelerator, is located in America, while the laser at Măgurele is in Bucharest. In practice, you have only two options. Either you build a laser next to the particle accelerator in America so you can do the experiment there, or you build a particle accelerator near Bucharest so you can do the experiment in Bucharest. If I'm not mistaken, the people at Stanford are actually building a powerful laser there to do such experiments. So, as I told you, it's a race. The ones in Europe, on the other hand, those working with the extreme light infrastructure laser or the Apollo laser, as we will see, they started from the premise that they wouldn't have a particle accelerator nearby, and they started from this idea. Let's accelerate the electrons ourselves with the laser. So, in other words, the ideal process would go like this. First, you use the laser to accelerate electrons, then you make those electrons interact with a laser beam. After that, in such a way that you get a high-energy gamma photon, and then, in the third stage, you make the high-energy gamma photons interact with the laser again. To generate electron-positron pairs using just the laser, there are three steps. First, I produce electrons, second, the energetic gamma photon, and third, the electron-positron pairs. First, the article we're talking about today is a collaboration between several international teams who used the laser from Măgurele and the laser from France. Apollon carries out the first two steps in this three-step chain to create electron-positron pairs. Here is the diagram of the experiment carried out both at the Apollon laser in France and later at the Măgurele laser. The Măgurele laser is currently more powerful than the Apollon laser in France, as we can see in this picture. In this picture, we see a laser beam on the left side passing through a region of ionized gas. In that region of ionized gas, they are accelerated by the laser, accelerating the electrons to very high energies through a process called laser plasma acceleration, which means accelerating electrons using a plasma. In English, this is also known as Wakefield acceleration. I read about this method because I had heard about it, but I didn't know much. Honestly, after all I've read, I still can't clearly explain how it works. So I'm gonna do it through the method of popularizing science and not through equations that I couldn't get through. I mean, they were very, very complicated and, well, in the end I said I really don't have that much time. I'll popularize science like others do. Yes, laser. Plasma acceleration is also called Wakefield acceleration, meaning Wakefield wake. I couldn't find a translation for this word in Romanian. It means something like delayed. Yes, that's what it means. And what you see in this image is the essence of the method, the Wakefield method. And what do we see in this image? Well, we see a boat, right, which creates some waves behind it, and on that wave there's someone surfing. Not all boats can do this. But you can buy some boats that create such big and high waves behind them that the person in the back can surf on those waves. Essentially, that's what I understood happens in the case of electron acceleration using this method. Namely, you pass a specific pulse, a laser, a very short pulse, through an ionized gas. What does it mean that the gas is ionized? It means that the electrons have been separated from the atoms and that a plasma has been created there in which the electrons can oscillate relative to the ions present. And what happens? When the laser pulse, a very short pulse, extremely important, passes through that plasma area, it creates a wake behind it in English, like the wave that remains behind a ship. It creates an area of electric field which is somewhat of a closed area, like a kind of cage. If there happens to be an electron there with the right speed, then that electron will be carried by that moving electric field cage, just like a surfer is carried by the wave. How is that electric field cage formed? Behind the laser pulse, I have to admit I couldn't follow the equations. Why that area behind the laser pulse in the plasma, that electric field cage area, follows the laser pulse? Again, I can't tell you. But what I understood is that it's very important for those electrons to be injected. Or protons, since you can also accelerate them with this method. They need to be injected at the right moment into that cage behind the laser. Behind the laser pulse, yes, and they need to be injected at a certain speed. That's what this image suggests, which tells us that essentially it's the same thing. From surfing, yes, because you saw when a person stands up to surf, yes, he doesn't just stand there, because if he did, he would go up and down on the wave and the wave would pass. To catch the wave, he paddles with his hands, paddles to gain some speed, and then he can surf with the wave. Well, and I understood that the same thing happens here, so you have to synchronize yourself. The laser pulse, yes, when it passes with the electron injection that you do, in such a way that the injected electrons, yes, to arrive exactly in that cavity that forms behind the laser pulse, and to arrive with the right speed, and then they stay there, trapped, and are carried forward and accelerated by that pulse, by that laser pulse. You might be wondering, well, the electron is moving behind the pulse at the speed of light, so where is it being accelerated? It looks like it's moving at a constant speed, right? I wondered that after recording the video, so I'm answering it now in audio. Usually, the electron is injected and already has energy in the mega electron volt range, energy that is greater than the electron's rest energy. So it's already moving at relativistic speeds, over 95% of the speed of light. Basically, the electron travels almost together with the laser pulse, and although it is being accelerated, its speed increases very little in absolute terms, approaching 99.9999% of the speed of light. There's no way it can surpass it. However, the accumulated energy reaches values on the order of giga-electron volts, meaning it becomes thousands of times greater. From what I understand, this is an alternative method of particle acceleration compared to classical methods, which was highly sought after at one point and will probably be sought after again, because powerful lasers are still being built. Its main advantage is that with this method, you can accelerate particles, electrons, protons, ions, and so on, to very high energies over very short distances. And now let's get back to our experiment. So we have a laser beam that creates a very short laser pulse, which passes through that area of plasma made of ionized gas. And thus, it creates a cage behind it. And that cage carries electrons, which it accelerates to very high energies and accelerates them to the right. And you can see in the design of this experiment, in the drawing, that the electron pulse that escapes passes through a magnetic area, and there a deviation appears due to the magnetic force. And in this way, the energy of these electrons accelerated by this laser plasma acceleration method or Wakefield acceleration can be measured. And we see that at Apollo, energies of almost approximately 1.5 giga-electron volts were obtained, while at the Extreme Light Infrastructure laser, Extreme Light Infrastructure, MP from Bucharest, from Măgurele, the energies are about 4 giga-electron volts, which, let's remember, are about 10 times smaller. These energies are about 1/10 those at Stanford Linear Accelerator Center de Reuil, which are roughly 40 giga-electron volts. We have passed both the first and second stages. It would be to generate a very high energy gamma photon with the help of these electrons, which now have a very high energy, through an effect called the Compton effect. The opposite. How did physicists using the Măgurele and Pei lasers accomplish this? Here we see the laser light, a laser which after passing through the gas encounters a mylar polyester foil. In that contact area, a plasma is created, and the plasma acts as a sort of partial mirror for the laser beam. That means the laser beam is reflected by that plasma area created in the polyester foil and bounces back. Where does it interact? Be careful with the electrons that have just been created by that laser plasma acceleration method. This way, we get the desired effect, right? Which one? The energetic electrons obtained by acceleration with the laser plasma acceleration method. Yes, they interact with the laser photons, which are from the laser at Măgurele. Yes, those are essentially the photons reflected by the polyester foil, which also had a small plasma acting as a mirror. So these energetic electrons, yes, will interact with the photons from the laser and will create a virtual electron, which then this virtual electron will decay. As a result of the decay, we'll get the energetic gamma photon we want. And we can see in this figure how they measured that indeed energetic gamma photons were obtained by adding a LANEX panel, as it says here. Yes, essentially, it is right in the path of the laser beam and the gamma beam, because that's what interests us. In fact, the gamma photons that come out there, and since they are photons, they are not deflected by the magnet, and they reach exactly, well, the detector. And here we see the final result. The gamma photons that were obtained had at Apollo an energy of up to 0.6 gigaelectron volts, and at the laser in Măgurele, up to 3 gigaelectron volts. These energies are, again, 10 times lower than the energies obtained in the FLAC experiment for the gamma photons. Which, well, is to be expected because the electrons that were generated here had energies 10 times lower. That was the second stage of the big experiment through which we want to obtain matter from light. And the end of the article. Because yes, it's an intermediate result. In the next stage, they should make these energetic gamma photons, which they have now obtained in the laboratory, interact with a laser beam. Also from there. Of course, the energy of the gamma photon is 10 times lower than the energy of the gamma photon from FLAC. However, the laser from Măgurele has an energy density hundreds of thousands of times greater than FLAC's laser. And then, in that process, the multiphoton Breit-Wheeler, the energetic gamma photon, will interact primarily with millions of photons from the laser beam, not just with a few. And that means it will generate many more electron-positron pairs. And with that, we've reached the conclusions. Tim, I would like to tell you a bit of my opinion, because otherwise I'll go on for too long. But the truth is that in Romania, and generally in the world, people are now looking for strong opinions. I mean, it's either bad or it's very good or very bad, and the reality is always full of nuances. And I think that's what's happening with the laser at Măgurele as well. Namely that the Măgurele laser was full of controversy a few years ago. And the laser at Măgurele remains, as I told you, essentially a European research platform. It is part of a consortium, yes, it has Romanian researchers and foreign researchers, and it receives projects both from Romania and from abroad. You saw how many foreign authors are on this article. And you saw that not only the laser from Măgurele was used, but also the laser from Poland. So, essentially, it is a research platform made available to researchers from all over the world. We in Romania generally look for exceptionalism. I mean, sir, is it the biggest laser in the world? And you saw that, I don't know if it's still the biggest laser in the world, because the SUV laser from China has already announced 8 petawatts, which essentially would be more than the laser at Măgurele, but that's not what's important. What's important is that I have 2 lasers, they're in the 10 petawatt range, and others will follow. And that all these lasers are at the frontier of knowledge. The experiment they conducted this time is one that belongs to theoretical physics, to fundamental physics. Specifically, how to get matter from light using the quantum vacuum. And I've seen many comments in the press like, why do we need such experiments? I mean, why don't we use the laser from Măgurele for practical things, cancer, medical issues, and so on? And it's true. If you check the website of the Măgurele laser, there are such projects as well. But there's nothing, absolutely nothing wrong with doing fundamental physics projects as well. Today he says it's actually normal. Because when you have an instrument that is very, very powerful, what interests you first is to make it work and see what you can discover with it. And after that, in the second instance, eventually, what are the applications? But in order to know the applications, you have to understand very well how it works. And in order to understand very well how it works, you have to do the fundamental physics things at the beginning. As for me, it was again a very, very hard-worked video. You may have noticed, I probably also had a short video on the same subject, which I don't know, maybe I'll put it here at the end. I worked very, very hard to do my research. I talked to people who know what they're doing. So the documentation took me a lot of time. I was glad because I learned new things, some of which I couldn't explain in detail the way I wanted. The acceleration, for example, of electrons and protons in plasma using lasers. It's not something I was able to go into depth about, but, well, that's how it is. But again, once more, it bothers me quite a lot because it takes me a lot of time. It's not just the research and gathering materials, but also the recording. Again, I don't know how many times I spend recording. I think it's about 3, 5, maybe 4 hours with a short break. and the editing, which I guess will also take a lot of time. That's how it is. That's how it is. I'll see how I can make these videos shorter. If not, any help from you is welcome. I'll end here. I'll say, I am Christian Presura, Physics Explained. I wish you all the best. Goodbye. See you next time.